Hello, this is a video on algebraic vectors. So we're going to do a comparison between geometric and algebraic ones. Geometric vector has no fixed location. So the way we could tell what the vector was, we had to quote the length or magnitude, and we needed to talk about the direction or show the arrow in which it's pointing. Algebraic vectors are drawn on a coordinate plane, and the tail has to be at the origin. Now, coordinate plane could be, for 2 dimensions, could be polar plane or Cartesian plane. We're going to be working with Cartesian plane, but I'm going to just briefly show you polar coordinates as well. So let's move the vector, geometric vector, onto the coordinate grid with the tail at the origin. So this particular coordinate grid has concentric circles, and the size of this radius could be read off of this by looking at, if this is radius 10 circle, this is radius 9, this is radius 8, so we're just slightly above that radius 8. And you can also estimate, so I estimated 8.4 units, I said here. You could also estimate the angle with which this vector makes with the positive x-axis in a counterclockwise direction. So it's roughly 54 degrees, I said. The way polar coordinates are quoted, they're quoted as radius goes first, comma, and then the angle is always in counterclockwise from a positive x-axis direction. Let's concentrate now on what we will be doing. The same vector is placed on Cartesian coordinates, which is what we're used to with x and y axis for 2 dimensions. And what we want to do is think about how these unit basis vectors are used to create this original red vector. So first of all, unit basis vector. So unit means size 1. So this I hat right here is a unit vector of size 1 pointing in the positive x direction. And j hat is a unit vector pointing in the y direction, in positive y direction. They form a basis. You're going to have a lesson about bases later. So if you were to stretch out I by size 5 and add that with a vector of j hat stretched out by roughly 6.8, because you can see how it's not really at 7 right there, then this vector green plus that vector in green will actually give you the vector red. So a b vector could also be quoted as 5i hat plus 6.8 j hat. Or there's another form for this. It basically looks like an actual point. If you did not have it labeled or named, you could not distinguish it in terms of its notation from a point. So it is super important for you guys to always record what is it equal to, so that it's very clear to the reader that this is a vector with a vector symbol above it. So this notation basically is mainly concerned with what is this vector pointing at, because as you recall, vectors could be moved as long as you don't change its size or orientation. If you move it somewhere else, it's still the same vector. And so if you put this vector with the tail at the origin, wherever it's pointing at, it's very unique. And so we can quote that with it looks like a point. We call these this version component form, or ordered pair form, or Cartesian form sometimes it's called. And then this particular one, there's also several names for this one. We can call it unit basis form or linear combination vector form. So let's start off with how to convert vectors in 2 dimensions. So I'm going to do this one right now. So algebraic vectors that we've already talked about, there's 2 ways to record it. Okay, a way that looks like a point and a way using unit basis vectors. And a geometric version where you have magnitude first and then the direction is quoted. So usually we would say northeast or something like that. It's 30 degrees to a tail of another vector or something like that. So it's always usually a little bit more awkward to quote it this way. Polar way is mentioned here, but you're not going to be asked to do anything with polar, so we can ignore that right now. So how do you go from algebraic to geometric? Well, to find the magnitude of u, all you have to do is use Pythagorean theorem on this right triangle, size a squared plus size b squared, all under the square root. And then to find the direction theta, which you should notice is close to the positive x-axis here, would be tan inverse of opposite over adjacent. So opposite of theta is b, and adjacent to theta is a. And that's it for that one. Then in order for us to convert the other way, I would like us to discuss how to record any vector using a unit vector. So we already talked about unit vectors that are standard basis vectors, I hat and j hat, but vector u has its own unit vector. I could call it u hat. So the reason behind the conversion formula for going from geometric to algebraic, I could record any vector by saying it is its magnitude and multiply that by the direction. Technically, this u hat is just the direction without the magnitude because the magnitude is just 1. Now, we need to figure out what that could be written as in terms of our theta. So I just went up here and redrew it. So this is size 1, so that's the u hat vector pointing up. We want to know what this size x is and what this size y is. Because this is a right angle triangle, we can use SOHCAHTOA. So if we use cosine of theta would be adjacent x over hypotenuse 1. And so x over 1 would be just x. Same thing with SOHCAHTOA, so the SO part, so we'll have sine of theta is y over 1, and so it's just y. So this vector u hat will be x and y as its components. And so cosine theta is the x component, sine theta is the y component. So you could leave it like that, or you could distribute the magnitude into each of the components and write it this way. So this formula will give you always the algebraic version. Just please be careful that this theta has to be counterclockwise from positive x-axis for this to work. We're going to do an example of converting two-dimensional vectors. We'll start with going from algebraic to geometric. So there are two geometric types, compass bearing, sometimes called the quadrant bearing, and the true bearing. Algebraic types are mainly these two last ones. Polar coordinates, I think of it mainly like a stepstone in between. It helps with conversions. So here's our question. It is -3i. It doesn't have the hat here, but it is implied. If it's using I, it's reserved for the unit basis vector in the positive x direction. Now, because there's a -4, that means we're going in the opposite direction of the positive x-axis, so in the negative. So -4 and up 3. So linear combination version is, I just record what they've given us. If you remove the vectors, the I hat and j hat, and insert a comma in between, that will give you this version, the scalar version, the one that looks like a point, but it's not a point because we can actually do operations with vectors, but we cannot with points. In order to convert, next, let's find the magnitude using Pythagorean and the angle in this triangle, theta. I found tan inverse. Polar coordinates, I call it that it has a math angle because it's mostly used for math class. We always quote math angles from positive x-axis and we go in the direction that's counterclockwise. So this alpha right here is the angle that we're going to use for polar coordinates if you ever had to do that. And when we convert geometric back to algebraic, we will have to make sure that we quote it in this particular way. So that's why I put this in as a discussion. And so because it's a straight line here, we know it's 180. So if we subtract 180 minus the theta, we would get our alpha. Vector A written in polar coordinates would be the magnitude, comma, the angle counterclockwise from the positive x-axis. If you were to write it in the usual way that we do so, in geometric way, we would say 5 units and then in words describe the direction, which is a little bit more awkward than this polar coordinates way. Moving on. True bearing. I think of it more like a physics angle because it's used a lot in physics classes or whenever you have application questions. So we have, it's an angle that's quoted from the north line, and it is going to go clockwise. So it's very different direction here, so be careful. So I put that here for comparison for you guys. This would be beta on the diagram that goes from the north line all the way clockwise until it hits this vector. And so that would be the 270 plus this theta, so 307 in the end. And so using this true bearing, you would say vector A is 5 units at a bearing of 307 degrees. And compass bearing, we have phi here. Phi here is going to be just how far is it away from the north line. And so we have 90 degrees minus theta gives us the phi, so that's 53. And so if you wanted to quote this in geometric way, using this notation, you would say 5 units, 53 west of north, or you could have recorded it N, 53, and then a W. Same thing. Okay, let's go the other direction. This is where polar coordinates will be helpful. So geometric to algebraic. So this particular one, here is the picture. It is 35 degrees west of south. So even though S is written first, the way we read it is 35 degrees west of south. So this is the picture for that. And V written in words is what I've already said. For true bearing, we want to go from the north all the way until we hit the vector here. So that would be a straight line, which is 180 plus this 35, so 215. And so you could say vector V is 7 units at a bearing of 215 degrees. For polar coordinates, we have to use the math angle, which is from positive x-axis counterclockwise, so this alpha right here. So we want to go to 70, but back a little bit because that's overcounting it by 35. So that gives us alpha. And so this would be how it would be written in polar coordinates. Okay, to convert to scalar or Cartesian, this is where this angle 235 is super useful. So you would say it is 7, that's the magnitude, times the direction vector, which is a unit vector. And so it's going to be cosine and sine of this polar angle that we had before. So I've already explained where those come from. And then just type it into the calculator. That gives us an approximation. So this point right here at the tip of this vector would be -4 units over and almost 6 units down. Okay. And then to write a linear combination, you basically take all of these components right here and just think of them as stretch factors on the unit basis vectors, like so. I do want to discuss with you that you do not have to use polar coordinates at all. I prefer polar coordinates. I'll tell you why. So first of all, you could have just said, okay, I'm going to just break this vector up into its horizontal component and vertical component. So because horizontal component here is opposite of angle 35, I would use SOHCAHTOA, specifically sine, and find this, this quantity. And this vertical one is adjacent to 35, so you could have said, okay, SOHCAHTOA again, and solve for that one. But notice when you do that, you don't have the negatives that you're supposed to have. You would have to look at your diagram and then decide yourself, do I need a negative there or do I not need a negative there? So this is the advantage of using this 235 angle, because it actually gives you the negatives that you will need. Okay, so this is what I wrote down, the polar angle. The math way of measuring gives you the sign positive and negative as needed automatically, which I like. Okay, let's go on to the next example. In this example, we want to take points A and B, plot them, find the vector, displacement vector between them, but then we want to reposition it so that its tail is at the origin. And we want to quote this vector in terms of what point is it pointing at, so that would be the algebraic way of quoting this vector. However, if this was a three-dimensional picture, we couldn't just read it off the graph like we can here. So I'm going to explain where the operation comes from, so that you don't just memorize but truly understand this, okay? So let's look at this general one. How do you find the related position vector of any vector between points? So because we want to move this vector to where an origin is, so let's suppose the origin is placed somewhere over here. So let's consider the vector O to A. So this vector O to A added with AB, because it's going to create a triangle here. We can actually find this addition of OA plus AB to be the vector O to B, because we start at O, we end at B. So that's our resultant. So we can say this is equal to OB. Now, because we're interested in the vector AB, just moved elsewhere at the origin, with the tail at the origin, we can reorganize this so that AB is isolated. So of course you can memorize this formula and just say, okay, it's always going to be tip minus tail, or the next where you end up minus the previous where you started from. But I prefer that you don't memorize but truly understand where it comes from. So let me show you another way of thinking about it. Another cautionary note, you cannot just say point B minus point A, because you cannot subtract points. So you have to actually think of it as a vector from the origin to the point with the vector symbol. Then it's valid to say subtraction between vectors. So just in terms of the naming, so this is, we could call it displacement vector because it's from one point to another. We reposition it with the tail at the origin. We can call this point, it's no longer B or A, it's pointing at some other point, but we can call it P, but this vector OP and vector AB are going to be identical. All right, so as I said, instead of memorizing this, here's what you could do. Take AB, and instead of thinking of AB as the direct route from A to B, go first to the origin. So go A to O plus O to B. So I sometimes call this that you uncollapse it or go the long route. Then, because vectors that look like points, they always have a tail at the origin. So this O to B is perfect because this OB vector is going to be having exact the same notation as this point B. But A to O is not in the right orientation. We want to have O first. So all you have to do is just put a negative in front of that one and swap the order OA. And so you could see that you get the same result as before. And so then you could just plug in the components of this vector, which look like exactly like that point itself, and then you can subtract. So you cannot be subtracting points, but because these are actual vectors, this is valid. And so this is how you would find out that this vector, once it's repositioned, is pointing at this point, even if you didn't have a grid to look at it and count the squares. A next example is to show you that it's not always just subtraction of OB minus OA, so you have to think things through, draw a diagram. So for example, we here have been given a parallelogram, OAPB. So when you're they give you 4 letters for parallelogram. It's when you go around the shape, it quotes every single point. So we have O, A, so P would be here, and then B. So we want to say find point P, and I'm not going to actually do it with numbers, just to show you the comparison. So I said here point P is going to be like the vector OP, so it's the one that's pointing from here at this diagonal of the parallelogram. And we know that OP is going to be an addition between OA and OB, because this is the law of adding vectors in the parallelogram way. So this is going to be OA plus this part right here, which is parallel to OB, and so you arrive at point P. So notice here we're adding OA and OB, whereas in the previous discussion it was a subtraction between the two. So don't memorize anything, think things through.